Good evening, all. Yeah, good evening, all. We'll wait for a couple of minutes for a few more people to join and then we'll get started. So before getting started, let me introduce myself. So I'm Durga Prasad. So I'll be the PA for this course Optimization Fundamentals for the upcoming next 11 weeks. So the main objective of these sessions is to help you understand some of the basic concepts. I'll be reviewing kind of a recap or summary of the topics that were discussed during the week's lectures, and then we'll also be discussing on a few problems that will help you solve your assignments. And if you have any questions, you can also ask them during these sessions. We will discuss those questions as well. We'll wait for a couple of minutes for a few more people to join, and then we'll get started. Yeah, I think we can get started. So this week's lectures mainly discusses again on the ones that we discussed over the last week. We start with the Weierstrass theorem, and then we'll also see what are the different types of minima on what basis we can classify them, and the usual type of constraints that we encounter in this particular course. And then we see what is Taylor's theorem, and we see how it's applied to derive the necessary and sufficient conditions for minimum. All of these are already discussed in the lecture videos. So I would recommend all of you go through the lecture videos for a full comprehensive ideas about each of these topics. I'll be quickly covering the summary of them so that it will help you to solve the problems that we will be discussing during this particular lecture. The first one, we start with the Weierstrass theorem, which we have discussed during the last week. So we have a set S that belongs to Rn. So this is it should be closed and bounded. So this is my domain. So S is called the feasible region. So our search variable or the parameters that we are searching for is X, and this X belongs to the feasible region. So whenever we mean feasible region, for example, if you consider y equal to sin X, S is basically X can be minus infinity to infinite. So this will be my search space. So we can always restrict this search space to be closed by where we already discussed what closed means. When we say it's a closed set, we need to have something like say minus pi by 2 to pi by 2. Why is this closed set? Because at this particular boundary, like if you take, we defined it last week as well, the difference between open and closed sets. In an open set, you can arbitrarily consider any ball thrown any point in that particular domain, and you will always end up finding a finite value of ball which encloses all the points within the same set. So how do we define the open set? So it's a set such that for all x, there exists an r greater than 0, such that if you consider a ball of this finite radius x comma r, and this will be a subset of S for all. This should happen for all particular x. Only then you call that an open set. And what is a closed set, which we discussed last week? Is if you take a complement of a given set, and if that complement is open, then we call it a closed set. So if we consider this particular one, what is the complement of this set? This is a complement of that particular set. And in this particular set, like say this is minus infinity and this is minus pi by 2, and again pi by 2 to plus infinity. Both are not included. I can consider any point, and I can consider ball. Ball here is in R1, so this particular function is in R1, so this will be a particular line segment. However, a small line segment I take, I can always choose an r greater than 0, so finite value of r that will enclose it to enclose the point, and all the points enclosed in that ball will also belong to the same set. So this is an open set. Since the complement is an open set, X will be a closed set. So this is what we mean by closed here, and it needs to be bounded. So what needs to be bounded? We are not talking about the function. So this S is the domain for which in which you are doing your optimization. So the domain needs to be bounded. So which means I cannot use something like this. So when I use something like this, X says minus pi by 2 to pi by 2, X is, there is a minimum and there is a maximum. So this is a bounded one. And similarly, the function that I'm going to use should be a continuous one. We have also discussed this last week. Why do I require it to be continuous? Because only when the function is continuous, we have a particular relation that holds. So when you have limit of f of xk will be equal to this particular thing holds only for a continuous function. And why do we need this? Because when we do the iterations, our sequence will actually converge to a particular value of x, and when that happens, we want the function also to converge. Only then we can say that the convergence is happening, and only then we can say that we can reach some particular value. And we also say that if something like this happens and you have a bounded set and a closed set, then you are sure that you will reach a minimum value, and like that particular domain has a minimum value, and you can also attain it, which means you can also find the minimum value as well as the particular value of x at which the minimum is obtained. So x star can be found as well as f of x star can be found. In that particular case, we denote it as infimum of f of x over x belongs to that particular set. Yes. And whenever this is whenever it exists as well as it is attainable, we represent it using minimum of f of x. From here on, whenever in the course you see this particular symbol when minimize f of x, it means we are inherently assuming that minimum exists and we can also attain it. That's when we use this particular form. Hope this is clear. Now there are different types of minimas which are also kind of important to be understood. So we know what a minima is. So the first definition is the common one. So local minima is an x star belongs to S. S is my domain. X star is said to be a local minimum if there exists an r greater than 0 such that f of x star is less than or equal to f of x for all x belongs to the ball and intersection of that particular S. So what does this mean? A particular point x star is said to be a local minima if you consider a ball around the x star in the neighborhood of the x star, the value of f of x should be either be greater than or equal to that particular value. So if you have something like this, so if the function value goes something like this and say this is my x star, so if you consider a point here, I consider a small region around x star. So the ball is considered the radius r. So in this particular case, this is a 1D function. So this is f and this is my x. So x belongs to r1, and let's say it's between some particular range, which I'm not worried about, but let's say it's closed and continuous. Sorry, it's closed and bounded. What we are worried about now here is, let's say this radius is some finite value around this x star. So we are considering the x star minus r, so x star plus r. This is my ball, and that intersected with my particular domain S. So for example, if you are in 2D space, my ball will be like a circle. So if I consider in 2D, then it will be something like this. Then what we are doing is so it will be a ball like this. So you need to consider both x and y values, but then when we are doing this intersection, we are ensuring that we are only searching along the x space. So that will be along only this space. This will be the domain on which you will be searching, and within this domain, whatever value of f you consider, all of them should be greater than or equal to the value at x star. Then we set x star to be local minimum. So in this particular case, what happens here? F at a neighboring point here is actually smaller than this one. So this is not a local minima. But if you happen to see a point here, then you can see that the neighboring points will have value either equal to or greater than this one. So this will be a local minima. And local minima is just one kind of minima that we can have. The other one is called a global minima. So the only idea is we extend the domain. So here we said that any finite, like however small it can be, even if a small thing exists, that at least one R exists, then we are calling it a local minima. But we are just expanding that if the particular ball that we are considering includes the entire set, the entire domain, then we are calling it a global minima. I think this is a straightforward thing. So here we are saying that it has to be a very small ball. However, small ball, even if it exists for r equal to say 10 power minus 9 or 10 power minus 8, then we are calling it a local minima. A global minima is when this radius expands to this radius is so large that entire domain is actually included in your ball. The next one is an unconstrained minima. Here we are not fixing on the particular domain. We are saying x belongs to Rn. So we will see this more in some of the problems that will come in the upcoming weeks. When we saw some optimization problem, we'll understand why when we use this unconstrained minima or why some problems can actually be converted into unconstrained minima in certain cases. We'll also see those things. The next concept is strict local minima. So here we have seen that the condition is f of x star is less than or equal to f of x. Clearly we say that less than or equal to is the important one, so it can either be equal to or something like that, which means when you have something like this, if the function goes something like this, all these points on the line will actually have f of x, like if you consider any neighboring point, the value of the function of those neighboring points will at max be equal to this value, or it cannot be greater than that, it cannot be less than that. The worst scenario is equal to them. And any neighboring points, if you consider, all these neighboring points will have a value greater than the points in this highlighted region. So these kind of points are satisfy the local minima concept. So even all these points are local minimas. But when we come to strict local minima, what we say that is equal to constraint is not satisfied. We want f of x to be strictly less than f of x star should be strictly less than f of x. So this doesn't qualify for a strict local minima. All these are local minima, but not strict. Something like this. So if you see something like this, if you consider this particular point, around the neighborhood of that point, I can find a ball of radius r such that all the neighboring points will have a value greater than or equal to this one. So this is a local minima. Similarly, if I consider a point here, that is also a local minima. Let's say you have something like this. Every point here, all the points that I consider on this domain will have more or less will have the same value of objective function. So all of them are local minima. But out of these conditions, so let's say A, B, and C, A and B, C, all are local minimas. B is the only one that is minimum of all the entire domain. So B is the global minimum. And the next one we are saying is we need a strict minima. So where it is not equal to the neighboring points, that is happening in case of A and B. So A and B are strict local minimas. The next concept is that of isolated minima. So what is the idea behind isolated minima? So here also it's the same thing. The only difference that we're seeing here is the x star belongs to the domain, and you should always be able to find some neighborhood such that in that neighborhood, whenever we say this there exists an r greater than 0 in some particular intersection of ball and with respect to s, what we mean is we are considering some neighborhood around the particular point x star. So in that neighborhood, sorry, this is also x star. So in that particular neighborhood that I have considered, I should have only one local minimum. So for example, if in this figure, if you consider a point A, that is a local minima, and there exists an r greater than 0, so I should be able to find some neighborhood, however small it is. As long as I can find some neighborhood, then it is fine. So here I can find a ball like this of some finite radius where all the neighboring points have values greater than the value at x star. So this is something that you can call an isolated minima. Even the same applies for even point B. Now, if you see the points in C, if you consider any point, there is some other point in that neighborhood. So whenever I consider a ball, there are some points which have value equal to this. So there are like multiple local minimas in any ball I consider. However small ball I consider, there will always be another point in that neighborhood which has the same value as the value at the current point. This is because of the flatness of this thing. So the C is not an isolated local minima. So A and B are isolated local minima, or let's say isolated minima. If you observe, what we are trying to do here is whenever you have like we are finding a way to differentiate between the regions that are flat and the regions that have curvatures, finite curvatures like the one that are shown here. And then now it is also proved in lecture. I'm not going through the derivation here. but I think it is fairly straightforward. You can see every isolated minima is a strict local minima. Whenever I'm saying it is an isolated minimum, it is something like this. It is the only local minimum in that neighborhood. There can't be any other local minimas, which means all other neighboring points will have values at max. All of them should be greater than the value that I have considered at x star. So that is the definition of what a strict local minima is. All the values in that neighborhood will have a function value greater than the one at x star. And that is what we are saying is the only local minima. So whenever it is an isolated minima, we can be sure that it is a strict local minima. Now, what about the converse? So can I say that every strict local minima is an isolated minima? Those of you who have already gone through the lecture videos might have come across this being mentioned in the videos as well, that every strict local minima is not necessarily. It's not necessarily an isolated minimum. And why is this? It can happen that in that particular neighborhood when you consider. So what we are saying is you have some neighbor, you have some function like this, and then you consider a point like this, and in that some particular neighborhood of that, there is no other local minima that is existing. This should be the only local minima. Then we are calling this isolated. But you can have some functions which go something like this, and this is my neighborhood. So if you see, this is one local minima, this is one local minima, there are three local minimas. Let's say 1, 2, 3. All three of them are local minimas. And out of these three, can I call any of them to be strict local minima? Yes. Yes, right? You can call them to be strict local minima because there is no flatness in that. All the neighboring points will have value greater than the local minima, greater than these particular points. So all of them are strict local minima. So they are both strict local minima as well as local minima. Now, because this is the radius, this is the domain I consider, and there are other local minima in the neighborhood that I have considered. These two or one or three, any of them, neither all of them, like you cannot call any of them to be as isolated minimum because there is another local minima in that neighborhood I consider. So there are certain functions. One of the examples is given in the lecture videos where you have functions like this with so many oscillations that are close to zero. One such function that is given is in the lecture videos is something goes like this. The point that we want to take is however small radius you can, however small neighborhood you consider, you will always end up with undulations like this. It's like this keeps repeating. However much you zoom, keep zooming into the picture, and you'll always find structure like this. So as long as this structure exists, you can never find a neighborhood. You cannot enclose only this particular thing. These undulations keep going on such that, however, like if you try to keep another thing here, like if you try to consider a neighborhood like this, then again, even in that neighborhood, you will see that there is a small undulation, even in that neighborhood. So this keeps going on, however small you go. So you will end up finding a scenario that this isolated minima that you are supposed to find will always be accompanied by two of these ranges. So which means the strict local minima can not always be an isolated minima, especially when functions have many undulations, many of these curves that can happen inside the function. And why are we worried about that? Because when we try to find some minima or something, so which of these things are we interested in? Maybe we will discuss that with the problem, so it will be better clear. So why are we worried about these different types of minima? What use does it come? Maybe you can ponder over it and then you can come up with an answer maybe in the next week lecture. And this is the general formulation of optimization problem from here on. So we are trying to minimize some objective function f over the domain x subjected to some constraints. These are called the inequality constraints because of the inequality, of course, that is obvious. And then you have the equality constraints. So these are M and M, P. So what are we trying to do is we have a feasible set, feasible domain in which we are trying to search and find find an optimal value for the objective function. Naturally, how do we represent this feasible domain? So let's say I have this is my search space. I'm not drawing the objective function here. This is just a search space. So say this is x1 and x2. These are my parameters that I have to search for, and my domain goes something like this. How do I represent this domain? We are denoting it using some relation. So somehow we have to represent this mathematically, and that's where these particular functions come. So say in this particular region, maybe I should draw something simpler so it will be easy for you to come up with the reason. So let's say, yeah, the easiest one that I could come up with, let's say you have a circle and I want to denote this particular region. So how do I denote this? There is some particular center A comma B and the circle radius is R. So if this is my feasible region, the entire highlighted one is a feasible region, and we will be saying x1 minus a square should be. Now here comes the equality and inequality thing. So if I just put equal to r square, if I just write like this, then it would mean that I am just representing the boundary of this particular region. So it will be just a circle without interior points. So it's like only the points that are lying on the circumference of the circle will be included in my feasible region, just the boundary. That is what an equality say. This is in 2D, but if you go into higher dimension, it would mean that you will be walking along some particular boundary or some particular surface. So in case of a plane, if you see in 3D, a plane is like a surface. So you'll be walking on that particular surface. Then you say an equality constraint. You can also, instead of that, you can always say something like this. Should be less than r square. This means all the points in the interior region, but not the ones on the circumference, because at the circumference it will be equal to r square. These are just the internal points. So when I use an inequality constraint like this, like less than or equal to, then it means it includes both the interior points as well as the boundary points. So this is just a way of representing the feasible domain. So some way we are coming up with to represent the entire feasible region. So I think this is clear. There are no queries in this. Okay. Now these are some notations that we'll be using throughout this one. So these will be helpful for your assignments also to compare your answers with the same standard notation that we'll be using throughout the course. So you have some function f that will be mapping from Rn to R, and x belongs to Rn. X is your domain. So when you say x is a vector, we denote it with a column matrix, something like this. And then fx is the derivative of f at that particular x hat, and that is we are representing with a row vector. You see the original vector is denoted as a column vector. Fx is the derivative is denoted as hi. Good evening. Yeah, I'm just going through some of the notations. So all these videos are recorded and will be uploaded on YouTube as well. Hope you have gone through the lecture videos. So just quickly go through the notations and then I will start problems in maybe like a couple of minutes. Yeah. So as I was saying, uh, the derivative is denoted as a row vector, and the gradient is there again is a vector. So we again use a column matrix for that. So that will be transpose of this. Now, if you have a function mapping from Rn to Rm, then we will denote that as a column vector again. So if you want to take derivative of this, then I have m of these values, and x again has n components. So the derivative of this particular function will be an m by n matrix. That will be something like this. And if I say Hessian of the function, Hessian is the double derivative of it, and let's say this is a scalar function. In that case, this is the notation we'll be using. So be consistent with the notation so that you'll be able to match your answers with assignment answers later. So like you might end up doing transpose of it, and then those might not match. Yeah, the next topic is the Taylor's theorem. This most of you might have already been familiar with. So we have a function. The first requirement is it needs to be differentiable. That's where it starts with. And then for a differentiable function, we'll consider some reference point A belongs to Rn. And there will exist a function h such that f of y can be written as f of a plus this is the gradient vector times y minus a plus h times y minus a. And the requirement is as and when you go close to the reference point, the function value h tends to 0. That is the main requirement of Taylor's theorem. So what do we have here? So just to put it in a slightly different way, so you can write this as, we divide it by minus a, that will be now if you apply y tends to a, this will tend to 0, and this will be fx transpose a, and this will be the derivative of it, which we already know from the previous thing. So as and when you go close to the reference point, the rate at which the value of objective function goes to the value at the reference point will be equal to the rate at which you go close to this one. So both will be the same at the rate that is defined by your gradient vector. This is a straightforward thing, and we will use this later to come up with all the conditions. I would recommend you to go through the lecture video to see the derivation of how Taylor's theorem is actually used to come up with all these conditions that listed down here. So the first order sufficient condition here again, we are saying that let x star belongs to S as an optimal solution. Let's say be an optimal solution of minimize f of x such that x belongs to S. So here we are saying S is open. So in the Weierstrass theorem, we said that S needs to be closed and it needs to be bounded and all that stuff. And if it is a differentiable, it will be continuous. But with these conditions, you cannot apply Weierstrass theorem directly. So that's why we are assuming that there is an optimal solution and we are calling it x star. So the existence is kind of implied in this one. So you cannot say you are assuming that it will exist in the first place, and if it exists, then it will in an open set you have to have this particular gradient has to be 0. Only if the gradient is 0, then you can have whenever you have an optimal, if you have an optimal in that particular domain, then at that particular optimal the gradient will be 0. That is what this particular condition states. Now, of course, out of all the such points that you do, you identified certain number of points where the first derivative is 0. Then how many of these values are actually the optimal solution? So this only says that if x star is optimal, then fx equal to 0. It's not the other way around. So x star is optimal implies the derivative of f at x star equal to 0. It's not the other way around. So wherever wherever the derivative is 0 doesn't mean all the points are optimal solution. So we need another condition. That's where the Hessian comes into picture. So this is your Hessian. Let's say h of x star. If h of x star is a positive semi-definite matrix, then you can call that particular x star to be a local minima. Right? So what do you mean by positive semi-definite matrix? So and see, this W doesn't have to be from the domain that we are considering. It can be, it belongs to Rn. It can be any vector in Rn space. For all the vectors, this has to be true, then it is called a positive semi-definite matrix. And then again, you can have several points where del square f can be 0, it can be greater than 0, or it can be equal to 0. Out of all those things, when you're sure that it is greater than 0, so positive definite is when you have it is strictly greater than 0. That is what we call a positive definite matrix. Only in that particular scenario, you are pretty sure that it is a local minimum. So if you have the gradient to be 0 and you have the Hessian to be a positive definite matrix, then that particular x bar is a local minimum. So these are the points that you have to search for in the entire domain. Everywhere in the domain, wherever the gradient is 0 and the Hessian is a positive definite matrix, are the points where you have a local minimum. Is clear? Are there any questions? Yeah, think there are no questions. Okay, so around half. Yeah. These are some problems that I would like to discuss. So you can solve them. I'll wait for a couple of minutes for each problem so you can solve and then we can discuss. Okay, the first one is straightforward. You don't have to solve anything. So what do you think? So if a local minimum is unique, then it is a global minimum. So what do I mean by unique? So if there exists only one local minimum over what? So when we say it is a local minimum or something, we mean only in the feasible domain, not everywhere else, right? So if there exists only one local minimum in the feasible region, then it has to be the global minimum. There is no other way. If you have multiple local minimas, then you have to calculate all the local minimas and then find the minimum out of all those minimums, and that will be the global minimum. If you have just one local minima, then it will definitely be the global minimum, right? I think there are no problems in this question. Yeah, let's take the second one. To have f of x equal to cos x for the domain x belongs to minus infinity to infinite has a unique global minimum. This is true or false? So cos x is something like this. Yeah, I'll just do a couple of things so you can type in the chat box or you can unmute yourself and fill the answer. Okay, it's not answering. So let me put it this way. Can a function have multiple global minima? So how did you define global minima before? See the derivation. If you see the definition here, the definition says that f of x star should be less than or equal to f of x for all x belongs to S, right? So it can be equal to, there can be regions of flat in the entire domain where all of the points can be considered as global minimum. So if you have something like this, some function like this, for this function, let's say g is a function of x, then all these points are both local as well as global minimas. You can also have something like this. So what about this? Let's say, it's not confused here, let's say something like this. So you have these points and these points. Let's label this A and B. A and B both are local minima, that is for sure. Yeah. So this is global and this is local, global plus local. So all global minima are actually local minima. That is straightforward. Yeah, so the answer is just right. You can have multiple global minimas. Somewhere you have something like this, a flat region, and you can say all global minima or local. Yeah, but if you see, the interesting point here is you can have all these points as global minima, but the objective value is a unique one. So the objective function, if you consider all these points, say x1, x2, so on, whatever points you consider on this particular highlighted region, all these points are global minima, but g of x1 equals g of x2 equals all of them. How many other points you consider? So just put 10 strings in. So all these points, the objective value will be uniform. So the value of the objective function will be unique, but the number of global minima will actually be infinite. So in this particular case, if you consider cos x will be something like, so you have something here. So this is 0 by the 2. All these points, wherever this becomes -1, all these points are local minimas, and since they are the value cannot be less than -1, all these points are also the global minima. So all these points, whatever points I put, let's say A, B, they are both local as well as global minima, because over the entire domain, the value cannot go below -1. So these are both the local and global minima. And you have multiple global minima. to have like it's from minus infinite to infinite, so we have infinite number of global minimas as well as infinite number of local minimas. But the objective function, the minimum value of the objective function is -1. That is a unique value. With that thing, so this doesn't have a unique global maximum, as you can see here. Are there any questions in this? Yeah, I guess there are no questions. Okay, we'll move on to the next problem. Yeah, from here I have a bunch of, say, a couple of questions that will essentially ask you whether you can apply the Weierstrass theorem for different kinds of functions. So if you recall, what are the main conditions for a Weierstrass theorem? So the function needs to be continuous. The domain in which you are searching has to be closed and bounded. These are the main conditions, three conditions in Weierstrass. So if I just write it down, first condition is f is continuous. The domain S is closed and S is bounded. These are the three conditions that we'll be looking in all the whenever I ask about Weierstrass theorem, these are the conditions that we'll be looking at. So in this particular case, which of these conditions are satisfied and which are not? So this is my S. X belongs to this particular thing is my S. F is 1 by X. So is S closed? There are definite bounds, and if you take the complement of this particular set, S complement is minus infinite to minus pi, both are excluded, union pi to infinite, and S bar is open, so implies S is closed, right? And what about the boundedness? There is a lower bound and there is an upper bound, so these are minus 5 and 5. Whenever we say boundedness, if you see the function value f as x tends to 0 will be infinite. So the function need not be bounded. We will come to that later. But here it's at x equal to 0, this function does not have a finite value. X tends to 0 plus, it has a finite value, 0 minus, it has a finite value, but it is not equal to the value at x equal to 0. Or in the way we defined in the last class, how did we define continuous function? Is you can consider a ball around that particular point, and however small ball you consider, there should be a point in the neighboring region such that f of x will be same in both these points, right? That's how we define continuous function. But here at x equal to 0, it blows up. So this is not a continuous function. This is closed and bounded, but not continuous. So you cannot apply, we cannot apply the Weierstrass theorem for this particular case. Let's take another problem. Again, let's take the same three conditions. F should be so this particular set 0 to 10 intersection 515. This is my S. So what is this? So you have zero to 10 is one, and 5 to 15 is another one. So the intersection is, this is my intersection region. So are 5 and 10 included or excluded in that? Right? 10 is excluded. 5, because it's not included here, that is also excluded. This is my set. So since 5 and 10 are not included, if is it a bounded set? Because 5 and 10 are some finite numbers, it is a bounded set. The function x cube plus 3x over the domain 5 and 10, 5 to 10 is a continuous function. There are no discontinuities anywhere. But if you take the complement of this set, S complement will be minus infinite to 5 included. If you consider this particular set, it is not an open set. S bar is not open. Because at particular point 5, so at particular point 5, if I consider a ball here, the ball has but some points here, some finite number of points here that are So if I consider a finite radius ball here, there are some particular points which are not part of the set itself. So around 5. So let's put 5 here. If I consider a ball around 5, x star is 5 of some small radius r, however small I can go. This is not a subset of S because it has points that are not in that particular region that I am considering. So it's basically in the entire real set from minus infinity to infinite, there is a hole in between. And when you have such kind of things, then it is not an open set. So this is not a closed one. If the complement is not open, it means S is not closed. So this is not satisfied. And because of that, you cannot apply the Weierstrass theorem. Okay. If these two problems are clear, I think you should tell me what is the case for the next problem. I'll wait for a couple of minutes so you can go through and let me know. Oh, the case. Okay, let me put those three things here. Yeah. You can tell me which of these are satisfied and which are not, and based on that, how whether you can apply Weierstrass theorem or not. Yeah. So what is my SS is this? Okay, let's see. So is F continuous? Again, what do you mean by continuous? Is there should be some neighborhood around around any point. If you consider a neighborhood in that particular point, you need to be able to find the value of objective function to be same on in that particular neighborhood. Same in the sense within a particular tolerance. So how do we put this? How do we say it is continuous or not? Is you should be able to find there exists an epsilon, or you should be able to do it for like at any particular point x, you will say the function is continuous. If in the neighborhood of x, you should be able to find the values of within some particular tolerance. So there will be some epsilon greater than 0. You should be able to find some particular ball around any point, let's say x star of a particular radius r. So in that particular neighborhood, I should be able to say that f of x star and the particular point that I considered should be within the epsilon I want, should be less than the tolerance that I have specified. So I can arbitrarily reduce this epsilon to 0. And even in that particular scenario, or like it will be like 10 power minus 8, 10 power minus 9, whatever it is, however small you can go, you will always find a particular point y in the neighborhood of x star such that this particular condition is satisfied. So this is basically, instead of saying this particular ball, you can say there is a neighborhood n. Or let's stick to the same notation as discussed in the lecture videos. And if this particular thing happens for all entire domain x, then you call that particular function continuous. Yeah. So what is with this particular function? Is this a continuous function? Are there any discontinuities in the domain? No, right? This is a continuous function. You can always find like if you specify some particular tolerance, you can always find the neighboring points around that neighborhood. You will have certain the value can always be approximated within that particular tolerance. This is a continuous function, and the domain is closed because if you take the complement that is open one, and it is bounded within -5 and 10. So all three conditions are satisfied. So this is where you can apply the Weierstrass theorem and say that you can always attain a minima in this particular domain. Now, as of now, we don't know what the minima is, how to calculate the minimum, all the stuff. All we can say is there is a minimum, the minimum exists, and you will be able to find that minimum. That's the only thing that we can say from this Weierstrass theorem. Okay, are there any questions? Yeah, we are halfway into the session, so we'll wait for a couple of minutes. So if you have any questions, you can ask. Yeah, I don't think you have any follow-up questions. Okay. Yeah, now let's see. Now when we saw about the first order and second order necessary and sufficient conditions, we saw that the gradient has to be 0 and the Hessian matrix has to be, that the derivative, double derivative has to be a positive semi-definite if then a local minimum exists. But for the sufficient condition, like to be sure that a local minimum exists, we need it to be a positive definite matrix. And we define what a positive definite matrix is. So now we should be able to calculate, given a matrix, we should be in a position to know whether this particular matrix is positive definite or not. So how do we do it? So let's take this particular matrix. So how did we define positive definiteness? So you say this matrix is for some matrix A. If W transpose AW is greater than or equal to 0, then we call it, so let's say, positive semi-definite. If it is strictly greater than 0, then you call it a positive definite matrix. So before even solving it, let me ask this question. Which of these two statements is true? All positive semi-definite matrices are positive definite. This is statement 1. And statement 2, all positive definite matrix are positive semi-definite. Which of these two statements is true? Or to those of you who like to do it in more visual thing, let's say these are positive semi-definite. All PST are PD. Or the other way around. All PST or PD is this, and all positive definite matrices are positive semi-definite matrices. Which one of these two statements is true? So you can see one is a greater than or equal to 0 and another one is a greater than 0 constraint. So if case 1 is satisfied, so if a particular thing is greater than or equal to 0, then the other one is always satisfied, or is it the other way around? So if you have a positive definite matrix, then it is definitely a positive semi-definite matrix, right? So if greater than 0 is satisfied, then definitely greater than or equal to 0 is satisfied. So all positive definite matrices will be a subset of positive semi-definite matrices, because there are some matrices for which this will be exactly equal to 0, which will not be positive definite matrix. So this particular scenario is the correct one and not this one. All positive definite are positive semi-definite matrices and not vice versa. Okay, now let's get back to this particular problem. So how do we do it? So there are two ways to do it. Okay, let's take one case. So how did we derive it? So we defined it as this, something like W transpose A is, so in this particular case, it's a 2D thing. So let's say take W to be W1 and W2. These are the two components that I need to find. And then my matrix goes something like this. And this is a quantity that I would like to calculate and check whether this is greater than or equal to 0 or not. Like what happens for this. So if you compute this, so you have, right? Something like this. So what can I say about this? Let me greater than 0, greater than equal to 0 or strictly greater than 0. What can I say about this? So maybe it will be clear if I just put it in this slightly way. So let's say I can, let's assume W1, like one of them is not equal to 0. If both of them are 0, then it's definitely equal to 0. But we are talking about a general case, like this condition has to be satisfied for all W, not just one particular value of unique case of a W. Let's take arbitrarily, let's take without any loss of generality, let's take W1 not equal to 0. So this particular thing will be, and this quantity is always greater than 0. What about the one inside? It will be something like 3 times some parameter x times x square. So you can write it as 1 plus, you can split it something like this. So this quantity is always positive, but this quantity can be positive, negative, or anything, depending on what the sign of, we assume W1 not equal to 0, this can be positive, negative, or anything. So it is the sum of two numbers, out of them one is positive and the other one is, could be anything. So this thing can be greater than 0, it can be less than 0, it can be equal to 0 depending on the value of x. No, it can't be 0, of course. Yeah, it can't be 0. But it can be positive or negative depending on the value of x. And you can always choose W1 such that the entire product can actually become 0. So you cannot be sure whether it is simply positive or negative or anything about it. So what we can say is it's not a positive semi-definite matrix. This is one way of going about. To those of you who are already familiar with the concept of eigen decomposition, you know that any matrix can be decomposed into something like this. So you have a matrix A, you can write it as something like this, where this sigma is essentially a diagonal matrix with the eigenvalues at the diagonals. So in case of 2D, it will be something like this. And you can, if you write something like this, and I say W transpose times A W to be calculated, you can always say it is, and this will eventually be some new W prime times. Okay, sorry, this is not A. This is some sigma. So it comes something like this. So if you expand, so this will be W1 W2. This will be lambda 1. So what would this give me? This now let's say my condition for positive semi-definiteness is strictly greater than 0. Or like let's get to semi-definite a little later. Like if we want it to be positive definite matrix, then we need to have this entire thing to be strictly positive, and lambda 1 lambda 2 are real values. So if you have a real valued matrix, then your eigenvalues will be real. Like if you have, then these values are strictly positive. W1 square and W2 square are strictly positive. So if lambda 1 and lambda 2, if both of them are positive, then this term over here is definitely, this is satisfied, right? If both lambda 1 and lambda 2 are positive, this is satisfied, not the other way around. So like you can have a very high value of positive lambda 1 and a negative value of lambda 2 and still end up having the entire thing to be greater than 0. So that this is not a very sufficient condition. This is not if and only if. If this particular condition is satisfied, then this is definitely greater than 0. So all you have to do is take your matrix, compute the eigenvalues, and see if both of them are positive or not. If both of them are positive, then you can say it is a positive definite matrix. Now let's say, now let me ask you. So can I say this is an if and only if condition? So it's necessary as well as sufficient condition. Let's say you have one positive value of lambda 1 and another one is negative value. Let's say lambda 1 is greater than 0 and lambda 2 is negative. And in this particular scenario, what would happen is you can always choose some values of W and W2 such that this greater than 0 is not satisfied, right? You can make it satisfy or you can make it not satisfy. But By our original definition, this has to be true for all values of W, not for only some specific cases of W's. Right? Yeah. So if you have something like this, then you can be pretty sure that if one of them is positive and another one is negative or something like that, then it is not a positive definite matrix. So maybe we'll solve this for the next case. So instead of solving in this particular way, instead of taking W1, W2, coming up with the equation, doing something, maybe you can calculate the eigenvalues and see whether they're positive or negative. So for this particular matrix, what are the eigenvalues? So all you do is that A minus lambda is 0. This is positive and this is negative. So one is positive and other one is negative. So this condition will not be satisfied, which means this is not a positive semi-definite matrix, right? Yeah, you can always say why not can we make it to 0? That like you can always choose some particular value of W1 W2 such that this entire equation becomes 0. But again, as just to re-emphasize, this condition has to be true for all values of x, not for some specific selected values of W, right? Okay. Yeah. If this is clear, maybe you can try the next problem. You can try both the ways, whichever one you are comfortable with. I'll wait for say 5 minutes. So I think 5 minutes should be sufficient to solve this one. Maybe you can do it the eigenvalue way. Or you can just take and check the equation. Whichever way you're comfortable with, and tell me which of these are true. Hi. Hi, good evening. Yeah, so I'm just discussing some problems. So this is about the positive semi-definiteness. So are you all aware of how to calculate whether a particular matrix is positive definite or not? Yeah, we can do it in either of these ways. Let's say we do the eigenvalues. We calculate the eigenvalues first. How do I calculate eigenvalues? That is pretty straightforward. You take A minus lambda, get off that particular value to be 0. And then from there you get the characteristic equation and then determine your eigenvalues. What would that be in this case? So 8 and 2 are my eigenvalues and both the eigenvalues are positive. So if all my eigenvalues are positive, then what can I say about the matrix A? We discussed just before. So if you have all the eigenvalues to be positive, then this particular equation will be positive for any W that I choose. Irrespective of the value of W I choose, for all values of W belongs to Rn, this particular equation will be satisfied. As long as this equation is satisfied, then we can call the matrix A to be a positive definite matrix. It is strictly greater than 0. Since both of them are greater than 0, I can say it is a positive definite matrix. If you want to confirm it again, you can always do it the normal way. So you can just take the W to be something like this, and you can compute what the value of this particular term is, W transpose AW, and see whether it is strictly greater than 0 or equal to 0, what happens. Maybe let's do it for one problem. So what would happen here? So what can I say about this particular equation? Is it positive, negative, or what can I say about it? Can I say anything about it? Maybe let's say without any loss of generality, I can say W1 is not equal to 0. Let's take W1 to be not equal to 0 and take it out. Maybe you can see how it proceeds somewhere. So it is something like W1 square. So what can I say about this particular polynomial here? Okay, let's make it equal to 0. So what will you get if it is equal to 0? What is the value of x at which this will be satisfied? Remember that we are discussing about this w, like essentially x is w2 by w1 and w is should belongs to Rn. In this particular case, W is R2, which means W1 and W2 are scalars. And if you solve this equation, what is the value of x you will be getting? You have equation ax square plus bx plus c. In this particular case, you have b square minus 4ac is how much? Negative, which means the both the x values that you are going to be getting are complex numbers, which is not in the domain that we are interested in. Which means this equation doesn't have a solution in the domain that we are searching. If you recollect from your, I don't know if maybe in your high school sometime back, so when you have a conic equation, something like x square plus bx plus c, with the b square minus 4 is a negative, and if a is positive, then this particular polynomial will always be positive over the entire domain. Or to put it geometrically, if you collect, so this ax square plus bx plus c will be something like this. If your a is positive, it will be something like that, and if a is negative, it will be something like this. Since there is no solution in the real domain, it is not going to touch the x-axis. So in this particular case, a is 8, 8 is positive, which means all the values will be greater than 0. So this particular thing will be strictly greater than 0. Since w1 square is also positive, and this entire thing is also positive, the product of those two real numbers will always be positive. So if it is positive, then we call that a positive definite matrix. If there is a possibility for 0, then we call it a positive semi-definite matrix, which is not the case in this particular problem. Instead of doing all this way, you can always calculate the eigenvalues and see if all the eigenvalues are positive, none of them being equal to 0, then you can call that matrix to be a positive definite matrix. Both are the same. Like all we do in this eigenvalue thing is we decompose this matrix A. Like if you are familiar with eigenvalue decomposition, you can do that. But for this particular course, you don't have to know all that at this point. So this method should also work. Are there any questions in this? Okay. Then maybe you can solve this problem just to be sure that you're familiar with the method. What can I say about this particular matrix? This is much easier to do with eigenvalue. Yeah, you can also solve with me so that once you have the answer, you can let me know. This is definitely positive, and 13 square is 169, so this is also positive. So I have both my eigenvalues positive, which means this is a positive definite matrix. We can also do it the other way and just confirm if you get the same thing. So did you get the same conclusion? So what is the equation that you got? Yeah, so what is the equation on which you came to the conclusion? So like if you can directly tell me the equation, I can write it down. Something like this, right? So I think the same thing applies as before. If you take b square minus 4ac, be 144 minus 16 into 9. So we got it to be 0. So you can actually get a perfect solution for this. Okay, how do you split this? Can I factorize this exactly? Since it's very okay. So we're getting the same thing. Only when W and both are 0, it will be exactly equal to 0. But the condition has to be true for all the values of W. For all values of W, you can say that it is a positive definite matrix. This is clear. Yeah. Next, the few problems are very straightforward ones because of to deal with the necessary and sufficient condition, we should be able to calculate gradients and Hessian and all that stuff. So this is just to check whether you kind of brush up your concepts and how you do derivatives and stuff. and also to be consistent with our notation that we have introduced in this particular course. Whenever we say gradient of some particular function, we denote it with a column vector. So there is a transpose here. We will stick to this particular notation throughout the course. So I have my function. So what is my gradient? Calculated at that particular point, and similarly this. Since these are, you might be already familiar with this, I'm not spending much time on this, but just to kind of brush up on these topics, just kept a couple of problems, and these are also there in your assignments in the first couple of weeks. Once the optimization starts, we'll actually take some real optimization problems and then solve them. So what is the derivative of this? So we have x plus with respect to y, and this should be evaluated at 1 comma 0. This leaves me, that is this. I don't think there are any problems with this particular thing. Okay, now let's see the next one. So now I'm considering a set C such that the gradient of that particular value is equal to 0. So what is the cardinality of that? Cardinality is basically the number of elements in that particular set C. And the first step would be to calculate the gradient. So let's take this one. So this is my gradient. So what do you mean by what is the set C? Set C is basically gradient equal to 0. So all we have to do is equate this to 0. So you have two equations, you and two unknowns. You have to solve for them, and you will be able to get the values of x and y. So what could be the before even solving? What could be the maximum cardinality of set C? You don't even have to solve that because we know that this is a linear equation, and yeah, it will be 2 because you have a linear equation, yes, and a quadratic equation. So you can have at most one x and two different combinations of y. What are the values of x and y you can get? Did you solve these equations, or you just saw from the equations and you kind of solve them? Yeah, so yeah, it can happen that this is a quadratic equation, so you can always end up with having both the solutions to be the same. In that particular case, the cardinality will be 1, which is not the case in this equation because you can directly see it right here. So you put x plus y minus 4 equal to 0, and the other equation will be x minus 4 plus y. So this term is 0. So y is 0 and 1. If y is 0, x will be 4. Y is 1, x will be 3. You have two solutions. One is 4 comma 0, and the other one is 3 comma 1. So the cardinality is true. This is straightforward. This is the last question I have for this week. So it's the same function. Let's calculate the Hessian for this function. Just to ensure that you are familiar with the notation. So how do I calculate del square f? Del f gradient is straightforward. Or let's just stick with the normal one. It's easy to write. So fx and fy. So what is Hessian? Should I write something like, I can always say I can do transpose and make it equal, but with our notation, which of these is true? Yeah, for a continuous function, you have fxy equal to fyx for a continuous and differentiable function. So it doesn't matter. It doesn't matter. The values will always be the same. But just to say that with the convention that we are using, which of these will be using? A or B? Let me just show the notation. So this is the notation we are using. As per this notation, what should my equation be? Which of those A or B will be my condition? So should I take something like this as a first row or something like this? Yeah, you have other elements also. Let's not talk about them for now. As per this relation, which one of them should I use? Fxy or fyx? Okay, why do you think so? So the notation goes like del xn times del x1, right? So del xn is okay. You are going with this notation. So if you are saying fxy, then you are meaning del square f by del x del y, right? Or you are going some other way around. Okay, I don't know which notation you are referring to. So maybe you're familiar with fxy. Okay, I'm when I mean fxy, I mean this particular equation, del x del y. You might be referring to the other one. Yeah, but as long as we are dealing with continuous and differentiable functions in this course, we don't have to worry anything about it. Both the values will be same. So it doesn't matter which one you choose. You already have the gradient. If you calculate the Hessian, what will be it? Fx with respect to x is 1. And you have to calculate this at 4 comma 0. So if you substitute 4 comma 0, you get this value. This is a very straightforward substitution. So I don't think you have any queries on this. Yeah, these are the questions I have for this week. So if you have any doubts, we can discuss them. So if you have any queries in this week lectures that you want to discuss, we can discuss them. Okay, then these are the questions I have. And that's the end of this week's session. So what we discussed are basically we discussed again what Weierstrass theorem is, when it should be applied, the three different conditions of continuity and the closed and boundedness. Then we saw what are the different types of minima that we have: local minima, global minima, and then we have isolated local minima and strictly local minima. Then we also discussed the types of constraints, the difference between inequality and equality constraints, how do you search inside the region and how do you search on the boundary. Then we discussed what Taylor's theorem is and how we can use it to derive the next necessary and sufficient conditions for minima in a particular domain, in an open set. These are the main topics that I discussed in week 2. As you don't have any doubts, if there are no further questions, then we can call it a day for this week. Okay, thank you. Thank you. Okay, then I'll end the session for this week. Thank you all. We'll meet next week at the same time, 5 to 7.